Okay. So today we'll continue doing polynomial regressions. I request you to type in the example 17.5, which is the data is in table 17.4. So let me take a screenshot of it and put it on my Excel sheet. Okay, so please type in this data and we'll then do the polynomial regression. Okay, so x, y, you want to type in 0, 1, 2, 3, 4, 5, and then 2.1, 7.7, 2, 9, 61.1. We want to do several things today, so I request you to be quick about this. Yes. Did you have a question? No. Yes.
Are we going to be having a participation thing?
Yes, we're going to have a participation thing, but this is not that thing. It will be a different thing. So please type in this data, and first thing I want you to do is try plotting it and see what is the trend generally looking like. So this is in page 474. If you go to that example 17.5, there is table 17.4. Please copy that data into Excel. So if you type in those 6 entries, x varying from 0 to 5 and y corresponding y values, we get 6 data points. And if you make a quick plot, what do you see as the trend? Would you say it's linear? It's clearly not, because the slope is changing from point to point. It actually looks like it's a good second order curve or a quadratic curve. So we are going to try and fit a curve that looks like y equal to a naught plus a1x plus a2 x squared. We are going to try and fit a curve of this form to this data. That's our goal with this data set. And last lecture I gave you like a quick way to set up 3 equations to solve for a naught, a1, a3. Let's recall that. Okay. What you would do is do a summation of all the y values that is equal to a naught times n plus a1 times summation over x plus a2 multiplied by summation over x squared. That is one equation that you can generate. And where am I getting this equation from? If you set up the error as the difference between the fit and the original data and go through a minimization process like we did for the linear fitting, you will get these equations. All I'm giving you is today is a shortcut to do this on the go without having to go through the full derivation each time. That makes sense to you? This is, if you remember where the roots are, you don't have to remember the intermediate steps. I'm giving you the final outcome. Okay. How will you generate a second equation? You would multiply by x, sigma xy equal to a naught times sigma x plus a1 times sigma x squared plus a2 times sigma x cubed. That is the second equation. And to generate the third, we'll multiply by x squared y equal to sigma a naught times x squared plus a1 times sigma x cubed plus a2 times sigma x to the fourth. That's our third equation. I'll give you a minute to write this on your notebook as well. So I'm sure you would have seen my email about the exam. I'm going to keep it open book, open notes. So no need to email me and ask, can you write on both sides of your sheet? Bring as many sheets as you want. Bring whatever material you can. And there will be two problems in module 3. One of them is going to be based on Excel and you responding to some questions. That problem could either be a linear regression problem with a transformation like we did last time, or it could be a polynomial regression of this form. Okay, so I'm telling you what you can expect. Either something like this or something with a transformation, like last lecture. Okay. And the other problem will be on interpolation, which will be only paper based. Yes.
So you want everything paper based?
Yeah, you'll have to finally use Excel to answer something on the sheet.
I mean, like for our notes to use on the exam.
You bring whatever you want, books, computers,
Okay.
PDFs, anything, everything is fair. All right, so now you need to compute these summations using the data. So you're going to set up additional columns. So you're going to set up a column for sigma x, which is the summation of x values, sigma y, summation of y values, sigma xy, x squared y, sigma x squared, x cubed, x to the fourth. So you'll have to add more columns, which I want you to do. So I'm going to write x squared, x cubed, x to the fourth, xy, x squared y. X into y, x squared y. X squared, easy enough. Take the x value, square it, square each entry and compute the values. X cubed, x to the fourth, xy, just 1 second, and x squared y. So please do these and check up against the screen if you have done it right. What is your question?
Do we count 0 as an n value? So do we have 6 ends or 5 ends?
0 is, this is not a counter, this is the value of x. So you have to include. You have to include the first row, which is 0, 2.1. It's a data point.
So n value becomes 6, not 5.
6, it's not 5.
Thank you.
See, the people who wrote the textbook, I don't know why their choice for x was 0, 1, 2, 3, 5. They should have shown you some decimal numbers to give you that sense. But it's a value of x, it's not a counter. Don't think we are counting from 0. We are it's, if you want, I can put number 1, 2, 3, 4, 5, 6. So if I do the sums, that will be count how many entries do I have? That is 6 entries. And then what is the sum of x values? What is the sum of x, y, x squared, x cube, everything? Sort of, let me, so. All right. Yeah, I by mistake wrote it here. Now I'm not able to hide it from the view. But anyway, so here's the key point. Are you seeing that each term in this equation comes from one of these sums? So sigma y would be this value 152.6. N will be 6. Sigma x is 15. Sigma x squared is 55. Sigma xy is 585.6. Sigma x cube is 225. X squared y is 2488.8 and sigma x power 4 is 979. So plug in these values, these coefficients, and set up three equations in three unknowns for A0, A1, A2. Go ahead, do that. So I'm going to do that also. 6 times A0 plus 15 times A1 plus 55 times A2 equal to what is sigma y? 152.6. So kindly look at this and tell me if you are not able to understand where these four coefficients came from. Make sure you understand it at this step.
The first 6 is the n value, correct?
Correct.
6A0, okay.
6A0 is
That first
n
value.
value. Sigma x is 15. X squared is 55. And then sigma y is 152.6. So please do this for the next two equations. All right, what's the second equation?
15A,
15A0 plus,
55A1,
thank you, and then
325A2
correct
equals 585.6.
equals 585.6. So that is second equation, and third equation would be
55A0
55A0, correct? 55A0
plus 225A1 plus 979A2
equal to
2488.8.
0.8. Pardon my handwriting. 2488.8. Something not clear? Where did I get the coefficient for the first equation?
Yeah, I see what I forgot to write down some of the stuff that I wrote down the first problem.
So how many of you all have seen that show House MD? House? You have seen it? Yeah, House MD. So in that, he says two things, everybody lies and also human error. Like the most common explanation for many things is human error. Anyway, so do all of us have the three equations with three unknowns? So now you can apply the method of your choice to compute this solution. If this were an exam problem, you have two choices. Either you could use one of the methods we learned in this course, or you can just punch this into your calculator and feed the answer. Suppose if it's a problem more focused on curve fitting, it's justifiable if you use your calculator to do this. But don't do that when I'm asking you, do it using Gauss Seidel. Don't punch it into your calculator and write one line. That won't work. Okay. One second. So if you're not using your calculator, what would be the quickest way to solve this like equation? What numerical method can I suggest you? If you do cross elimination, the problem is this equation looks messy and you will have to do a lot of algebra to get a solution. If you use Gauss Seidel is a nice method if you have a computer handy, but it's not fun to do it manually. So I'm going to suggest you a method which is actually very easy to do directly, like by hand, and that is something I recommend that you use when you are doing this in the exam. Like it's called Kramer's rule. Okay, we'll quickly see what the method is, but before that, you had a question.
That's my question.
Thank you. So I'm going to stop the share here for a second and let's learn Kramer's rule. Okay. So Kramer's rule. The easy method actually. So if you have an equation of the form Ax equal to B, in our case, can somebody tell me what is Ax or the matrix A?
Upper left cross.
So I want the coefficients of A0, A1 and A2 in that order.
6, 15, 55,
Okay.
15, 55, 225, 55, 225,
979.
97.
Okay. So this is A multiplied by my solution vectors A0, A1, A2 or variables A0, A1, A2 equal to B, which is what is the right hand side coefficient?
152.6,
152.6.
585.6, and 2488.8.
Thank you. So this is a compact notation of your three equations in three unknowns. The one you just derived, I've written it in matrix form. Okay. Kramer's rule, not like a deeply theoretical technique. I'm just going to give you 3 steps. Step 1, compute the determinant of A. You know how to compute determinant, which in this case is 6, 15, 55, 15, 55, 225, 55, 225, 979. Step 1, compute determinant of A. We'll give it a symbol. We'll call it delta. Okay. Delta equals determinant of A. It will be some value which you can easily figure out. For now, let's leave it blank. Step 2, if delta equal to 0, this implies the system of equations has infinitely many solutions. And if delta is non-zero, then it has a unique solution. Compute delta 1, which is defined as, do you already know about Kramer's rule? Like yeah. Do you want to say what's the next step here?
I don't remember. I did.
Anyone else wants to take a chance?
As far as the formula was?
Yeah, how will you come? See, you'll have to replace first column with vector B. If you want to compute delta 1, replace the first column with B. And keep the second and third columns the same as what they are. 15, 55, 55, 225, 225, 979. That is delta 1. Okay. And A1 or in our case we'll call it delta 0 because this corresponds to A0. A0 equals delta naught divided by delta. So this will be a number, this will be another number. You just have to take delta naught divided by delta. That is your value for A0 in one step. So let's catch up on the writing, then we'll continue. So delta 1 corresponding to A1, delta 1 will be, keep the first column, replace the second column with this vector. 6, 15, 55, and then 152.6, 585.6, 2488.8, and third column is still the same. 55, 225, 979. This will be another number. A1 is delta 1 divided by delta. So I'll write it out here. Replace column 1 with the column vector B. Here, replace column 2 with column vector B. You're confused, this is A and this is B. And you can see where this is going. Delta 2, which corresponds to A2, is equal to 6, 15, 55. What's the second column? 15, 55, 225. And replace the third column with column vector B, 152.6, 585.6, 2488.8. And you would write A2 equals delta 2 divided by delta. Now go ahead, compute 4 determinant values. Delta, delta naught, delta 1, delta 2, and get me the values for A0, A1, A2. A0 equal to, A1 equal to, A2 equal to. Go ahead, do this. So I hear a lot of coughing in the class. How many of you all got your flu shots? You did? Does that mean most of you all haven't? So I know you're very young and you're very robust and everything, but please get a flu shot. It'll save a lot of time for you. It's not that you can't withstand a flu, but at least it'll save you time. So all right. Is anybody able to get these numbers? Yeah. All of you? I mean, if you do the steps for Kramer's rule, which effectively involves 4 steps, calculating 4 determinants and then calculating the quotient of the delta 1 over delta or delta 2 over delta. So it's a fairly easy method to use. If you are able to assemble this spreadsheet, the table with x squared, xy, all those values, and the sums, and you type in the value of your coefficients a0, a1, a0, a1, a2 here, and then let's go down here, click on the graph, add trend line, and in the trend line, you already have a linear, okay? Instead of linear, select polynomial and order 2, display the equation and the r squared. Let's make this bigger. So the r squared is nearly 1, which is a good thing. So the constant term is 2.4786. Our a0 is 2.4786. If you round off everything to 4 decimal points, 2.4786. And then second term or the linear term is 3593, and then the quadratic term is 8607, which we also get. If you are able to get all this in one place, okay, save your file, give it whatever name you want. I'm going to create like a upload, like a submission portal. By 12:45, please upload this file with this sheet.
What did you do to get that graph?
Right click the data point,
Yeah.
add trend line, and then in that, don't click linear, choose polynomial of order 2.
And we're using X and Y as our data set.
Yes, X and Y. Yeah. So please do 3 things. One is it should have the table with the sums. Number 2, it should have the coefficients which you calculated using Kramer's rule. Number 3, it should have the trend line and the equation displayed on the chart. So if you have these 3, save it. I'll create the file portal Dropbox. You can upload it for your participation assignment. Yes.
Just having a little problem, so you can make
I'm sorry.
Okay, so I found Kramer's one, and I'm just doing general numbers, and they were doing.
What is this?
This is for doing Kramer's.
Okay.
So this is my like A0, A1.
Okay.
And these are clearly not right. When I solved for Kramer's,
Okay.
diagonal, so I like together each of the components, and then for this one I did diagonal.
Why are you doing that?
This particular terminal.
Okay, that will work. Doing the diagonal for the determinant will work only if it's a diagonal matrix. Not for any matrix, not for any
Okay.
general. If you have to do the expanded term by term, so 6 times subdeterminant of this minus 15 times subdeterminant plus 55 times the 2 by 2 determinant. You have to expand the.
Oh, yeah.
Just this one page, save a file, keep it ready, and when I get a chance, I'll create the poster.
Can you
So I'm
move
giving
the
you
graph out of the way
2
so I can
minutes
see?
here to kind of wrap this up, and so that we can move on to the next thing on my agenda.
Is this in the file posted for last class?
This is something we started only today. it was in the first few minutes that you couldn't join. So maybe you can take up to 1 o'clock to email it to me.
Okay.
You're curious, that student has a situation for which I'm allowing him to participate remotely, but this is not something I generally encourage for everyone. I want you to come to class. Oh, good. It's good to go. So I just need to make sure it can accept XLS file, XLS or XLSX, and you can try now. So it will be open until 12:45. You can upload the Excel file that you generate for this example. I'm going to start on my next topic in like 1 minute. If anybody wants time, you have to tell me. Otherwise, I'll start.
Can you do me 1 second, please?
Sure.
Thank you.
Let's see how many have started uploading. Four people have uploaded. So let's try to see if more people will upload in the next 2 minutes.
On our exam, how much of the Kramer's rule work do you want to see?
If you just write using Kramer's rule, delta 1 equals whatever value, 4 values, and the values of A0, A1, A2, that's the number. You don't have to write out every step.
You don't want all of the arithmetic math between the start and finish.
No,
Everything, just.
no, that is, I'm doing it here to explain it, but you can be brief about it. Yeah.
Could you just go back over how to get the A1 values? Just really confused that.
So A1, it's the second variable in our list. So you would replace the second column with the column vector P, and then compute the determinant delta 1. And A1 will be delta 1. This is always numerator divided by delta, which is the determinant of the coefficient matrix A.
Okay.
So it's like, if you want the first variable, replace the first column. If you want the second variable, replace the second column, third variable, third column. And ratio of the, we'll call it modified determinant versus the original determinant. Yeah,
So when we're doing this online exam at home, we need to see the individual steps and we're
that's what he also asked. You can be brief about it.
Okay.
You can be just write 4 sentences, delta 1, delta 2, delta 3, and A0, A1, A2. That's it. See, you will see that, 1 second, if you will see that as this course progresses, whatever you learned in module 1 will be sort of compressed in module 2 in 1 sentence. Whatever you learn in module 2, when you go to module 5, it'll all be compressed in 1 line. Like we are doing this interpolation, we'll write 1 sentence and do the outcome instead of writing out all the steps of how to do interpolation. So you will see this becoming boxed in more and more. After a while, when you get to your professional practice, or if you go into research, you'll be like, the contents of this entire course are compressed in 1 sentence. So whenever my students tell me I have to solve this equation, I'm like, yeah, sure, go solve it. Don't tell me how. all the numerical methods you learn here eventually become part of your tool set. You won't talk about it, but you'll keep using it.
Do you just want one submission, or is it okay if we,
Why do you need multiple?
because Mike's making the graphic, he broke it, so I don't think there's.
Fine, go ahead,
So,
whatever. Okay, so I'm moving on. Is everybody okay with that? You will upload this file and we can continue on. All right, thank you. So one aspect that we still want to discuss about this fit is how good is the fit? So how do you estimate that goodness of the fit? You can compute. Your attention please, this is sort of important. You can compute a quantity which compares the fit minus the data. Y fit minus Y, or Y data minus Y fit. I'm going to delete this. Don't delete this. Still make. All right. Y fit minus Y data. How do you calculate Y fit? If you want to do the calculation of the fit values, how would you do this? You would write A naught plus A1 times X value plus A2 times X squared. That's the idea of the fit, right? To put in the values of the fit constants and the X value so that you can reproduce the Y value. And what is Y fit minus Y data, or Y data minus Y fit? Can you tell me and say which columns should I subtract? Which is Y data here? Y, so that is D7 minus J7, right? D7 minus J7. D7 minus J7. So that is the difference between my fit and the original data for the first entry, and drag it down to get the remaining entries. Oops, sorry. I have to lock in this. Yes,
You should,
right. So it will be, I have to take my B1 plus B2 times X plus B3 times X squared. B1, B2, B3 must be frozen, so you press F4 so that you get that double dollar sign. You can also see it here at the top. Oh, that's hard to see. So somehow I'm not able to magnify that. So let me do it again for you. So B1 equal to B1 press F4 plus B2 press F4 multiplied by X, which is C7, plus B3 press F4 multiplied by X squared, which is C7 squared. A2 times X squared, correct. So then you drag the calculation down to several levels or the next few rows. And the following column K is the difference between your data and the fit. Ideal, what does the ideal fit look like? If the fit were perfect, what would be the values of this difference column? Zeros. But that won't happen because real data always has some noise, so there is always some shifting around. So this will be a number, but you want this number to be as small as possible. If you are able to get up to here, let me know and we'll do the next step.
Is there a reason why we're doing it C7 squared rather than using E7?
Yeah, you can use B3 times E7, that's fine, since you already have it, you might as well use it. Okay, are we all together? You have up to this K7 through K13 values ready. So next what you do is, we'll call this difference, and then you do difference squared. Just square the value that you have here. Square it, and then compute the sum of that difference, or sum of the difference squared, 3.74. So if I want to write SR equal to summation I equal to 1 to n yi minus a0 plus a1 x plus a2 x squared, and this whole squared, that SR is this number. It happens to be 3.7466. This is your SR. Okay. We need SR. That's why I'm making a big deal about calculating it. We are going to use it in the next step to estimate the quality of this fit. Okay. Are we all up to here? SR 3.7466. Okay. So the standard deviation of the fit, we'll write it as S y bar x, that is equal to SR divided by number of observations minus number of parameters, square root. Take a break from writing, I'll give you time. We just estimated what is SR, which is the difference squared summation, or sum of the difference squared. Denominator has n, which is number of observations. How many? What is the number of observations here? 6 observations. 0, 1, 2, 3, 4, 5, 6 observations. How many fit parameters do we have? 3 fit parameters. We fitted it to A0, A1, A2, right? When you did linear, how many fit parameters you had? 2, A0 or M and B, slope and intercept. If you did a fifth order fit, it will have how many parameters? Fifth order fit, fifth order polynomial. What is the general form of a fifth order polynomial? Louder, please.
A0 x to the 5th plus A1 x to the 4th plus A2 x to the 3rd.
So you can count it like you have to go from x power 0 to x power 5, which is 6 degrees. Or you have 6 fit parameters if you fitted a fifth order polynomial. So m is just the number of fit parameters, which in this case happens to be 3. So I'm going to write, in our case, this is SR, okay, n equals 6 and m equals 3. Number of fit parameters or fit constants, and this is number of observations, and SR is sum of differences squared. Okay, sum of differences squared. So I'm going to write S y over x is square root of this number divided by n minus m. So this is standard deviation of the fit. So please compute this number and I'll tell you what this number actually means. So if you take SR depends on how many observations you make. So because it's a summation over all the observations, if you made 1,000,000 observations, numerically this number will look bigger. Would you agree? If you have to, let's say you have a difference of about 0.1, but you add it 1,000,000 times, it's a big number, right? So you have to normalize this by the system size or in proportion to the amount of data you feed, which is n. But within that n, not all of them are freely, you can choose them freely. You have to subtract the number of fit constants that you use to summarize your data. So the effective number of observations is, you have 6 observations and you are fitting them using 3 constants. So 6 minus 3 is 3 free observations that you have, which is also called degrees of freedom. So I'll write n minus m is also called degrees of freedom. In it's good practice. It's good practice if n minus m is greater than 10 at least when designing experiments. Who can explain or who can comment about this sentence I put in here? It's good practice to have at least 10 degrees of freedom when you are doing experiments. Have you taken any lab course yet? Fluids lab, heat transfer lab. So in fluids lab, which I've taught a few times, you would have one experiment where you drop a sphere through shampoo or some viscous liquid and then measure its settling time and then use the settling time to calculate viscosity. Now recall, if you've already taken that course, how many times did you repeat that trial of dropping the ball, recording the time and making observations in your notebook? Yeah, how many times did you repeat each trial?
I think once.
Just once? Okay, whoever is
In each different shampoo, we did it one
just once?
or 3 in our case.
You probably did 3 or 5, not 1. Okay, forget. Maybe we'll give you one other example.
Use my left partner. Says 1 too.
I think it's one, yeah.
Then that is a different problem to deal with. You come to Can you think about this sentence and tell me what does degrees of freedom actually mean? Like
Effectively error.
sorry?
I mean, effectively is it just error with another name?
No. So think about this. If you were to sit outside and for 30 minutes, your task is to count how many cars pass the Zach H. Sterling and Central Avenue intersection. Just sit there, have a clicker in your hand, and you have to count each time a car passes. So suppose you do this for 30 minutes. Okay, and you do this for 30 minutes between midday at midday, and you record, let's say, 55 cars. If you repeat this experiment at midnight, what will be your observation be? Like let's say 5 cars. Okay, and if you do this at 8:30 a.m., maybe it will be double that number. So how many times? So if we call each observation, that is one observation is defined as sitting there for 30 minutes and counting how many cars. So each observation will give you one number, which is the number of cars. So my question for you is, how many times should you reasonably do this trial? Like how many times do you have to do these 30-minute countings in order to get a reasonable average of what goes on at this intersection during the day?
Like for their time,
Yeah,
30,
30 times,
like 48 times.
48 times. Can you justify your numbers, choices, 30, 48?
Back in high school, I took a stats class and it says like n should always be at least 30.
Why? It is correct. Why?
Because the statisticians told me so.
Okay. You will be a good manager, I think.
I was an expert, so like, isn't that what we're supposed to do?
See,
No.
if anyone can take decisions. Politicians always take decisions because they have power. They are informed by experts. Supposedly, by doing engineering, you are those experts. You can't act like those politicians. You have to have the technical capacity to see what is the hard facts, and then decision is a much more complicated process. Okay, so you have to find out why 30. You are going to say something?
You wanna have more, a larger sample size, because that's going to let you see the same conditions. Or the same situation under different conditions, which can affect kind of random fluctuations, and it, like, there's a traffic jam over here, you get fewer cars. Traffic's rerouted, more cars, and the more days that you take that sample over, the more you're going to get an idea of what it's expected to be at any given time.
Correct. That is, to put it in another way, suppose you do a trial today and your bad luck, today happens to be the day where it's bad weather and no driving takes place in this road, you will record 0, but is that a fair assessment of that road for the entire year? Of course not. So you have to do it many times to cover for random variations, right? So when you do that, you said 30, right? 30 degrees of freedom, or in other words, if you are trying to measure something and summarize it as an average, meaning your 30 observations or 50 observations are summarized as one number. So the number of degrees of freedom in that case is 30 minus 1 being 29. In this case, you did so measuring a single quantity, like measuring number of cars, or measuring a voltage 20 times, or measuring the settling time 5 times, that is just one observation you are summarizing. Sorry, that is just one parameter you are summarizing. 5 observations are summarized as a single average. So in that case, the degree of freedom is 1. Here you are measuring 2 quantities. You are setting X and also measuring Y. So there are 2 pairs, so two quantities measured simultaneously, and they are summarized using 3 fit constants. So m equals 3 or m equals 4, depending on what kind of fit you choose. After you account for the number of fit constants into which the data is summarized, you should still have enough free variables or free or quantities remaining, so that this experiment can still be considered to be having a large enough sample set. If you just did, I'll give you an example just with this data. If you look at this data here, second order fit looks very reasonable. What does a linear fit look like? It's still not bad. It's like 0.94. And if you are satisfied with the level of information that my Y increases with X, of course, a linear fit also suggests the same. You are satisfied with that level of information, this is a decent fit. If you want to be very precise or very quantitative, this is the better fit. But why stop at 2? Why can't we do third order polynomial? Or why can't we do a third order polynomial which still looks even better? Or why not look at fourth order polynomial or fifth? So something happened between 4 and 5. What's the problem with this fifth order polynomial? You have to be louder.
Is the problem that we added another A value?
No, it's not that. Look at the curve. It's as though like you are connecting them data point by data point and trying to over constrain the problem. You are trying to say that you have a fifth order polynomial. I told you have 6 degrees of freedom and we have only 6 observations. So if you are tying 6 observations with 6 degrees of freedom or 6 fit constants, you don't have any free variables left. You don't have any freedom for these particles to show their feature. You are over constraining the problem. So differing to the wisdom of statisticians, people came up with the number on 30. It's just what you said was actually perfect. I'm just having fun with you. Okay, don't feel bad. Statisticians came up with the rule of 10, and the way they came up with is that if you take this standard deviation SYX, okay, and if you want this to be a small number, having 30 in the denominator, roughly 30, will ensure that regardless of what your standard deviation is, you will get a small standard deviation. That is where the 30 is coming from. It's a reasonable number because not every experiment is equally costly. Some experiments are very costly, like doing a settling time measurement 30 times takes more of your time. Or if you have to stand there and do the car counting like 100 times, that takes a lot of time for some person to do it. So making 1000 voltage measurements on the other hand is very easy. You can easily automate it on a computer. This can be done using LabVIEW or other measurement software. That's easy to do. So ideally, if this number is infinity, that's good, but infinity is impractical. So 30 is sort of like a happy compromise, which is neither too large, nor too small, not too costly for most situations. You would be interested to know when people do biomedical experiments with animals, if you have to get data on 30 animals, that will blow up the project cost like by orders of magnitude. They try to do experiments on 6 animals. You're trying to get the average of a quantity using 6 data points. That leaves you with 5 degrees of freedom, 6 minus 1. So people choose their number of observations depending on how costly or easy is the observations to be made. So 30 is true, is good, but it's not a universal answer. If you go to biomedical engineering, they'll say 6 is a good number. With the same sentence, except instead of 30, they'll say 6. Okay. So it depends on where you are working at. In electrical engineering, they'll be telling like 1000 observations. Acquire 1000 voltages, which can be done within a second. It's very easy to do. You would have learned it in your circuits lab. Okay. So this degrees of freedom is a concept that you should be aware of, and we'll explore this even more in module 6 when we do statistics. Okay. All right, so with this, I'm going to stop with Excel. Okay, I hope many of you have finished uploading. And if I see here 28 submissions, that's pretty good. We have a class of 32, so that's good. And then I want to switch to MATLAB to show you a couple of things, and then we can kind of wrap up curve fitting. Any questions before we go forward? So in MATLAB, please go to the documentation or the help bar here and type curve fitting app. It'll show up this app called Curve Fitter. Click that and wait till you get this window. Okay. So if you go to your command prompt or command window, I want you to do what I do. If you already are not familiar with MATLAB, type in x equal to 0, 1, 2, 3, 4, 5 and press enter. I hope this is big enough.
Are we supposed to do the polynomial curve fitting? Is that the one?
Yeah, we are going to start there and do something else as well. So for those who are already not familiar with MATLAB, go to the command window, type x equal to this, and also y equal to the data that we just handled, which is y equal to 2.1, 7.7, 13.6, 27.2, 40.9, 61.1, and press enter. So please do this. I'll give you a minute to open MATLAB. Do this.
What are we supposed to do before the command window?
Go to the search bar, type curve fitting, and open that app. For this exam, no MATLAB, okay? This exam. Third exam, we'll definitely do MATLAB. Yes.
You talking about the search bar on the top, right?
Yep. Type curve and it'll show up the first result. So if you go here, type curve and click on that first result, apps curve fitter. Okay. Do we all have this app and the X and Y entered? Yes? No? Okay, so maybe it means you haven't installed it in your MATLAB package, so you can add those. I wanted to show you this tool that MATLAB has and also use it to teach nonlinear regression instead of doing, the derivation by hand. This is getting recorded, so I hope you can go home and try this, okay? But don't sweat about this. This is not going to be something on which I have a homework or a exam plan. So this is sort of like learning. Okay? All right. So for those who are trying this, go to the fitting app, okay, and let's say a new session. Let's get a new session. There is, so far you have been learning all the concepts behind curve fitting. Now we are going to ask the computer to do it, assuming that you know the concept. Okay, so all right. So then in this, select data. Click select data. And my X data should be my X values and Y data should be the variable Y that I created. Y data is Y. And immediately once I do that, MATLAB shows me the raw data and a suggested linear fit. Linear fit is no good, we already saw that. So what you're going to do is to go to this fit options. The degree of the polynomial, we want it to be 2 instead of 1. So if you do 2, MATLAB has already finished doing the calculations. So if you see at the bottom table of fits, it shows what type of fit, R squared, 3.7466. That sounds familiar. That was the summation of S squared that we computed, remember? So that is this value. And what are the values of A0, A1, and A2? So if you see here, let me make this bigger. No need to follow this, like no need to do this right away. I'll give you time. see the results here. So the polynomial fit curves template is P3 plus P2x plus P1x squared. We had it backwards. We call this A0, A1, A2. You should not be, confused by that. P3 is our A0, 2.4786. P2 is our A1, 3593. P1 is our A2, 8607. The same values. Okay. MATLAB is very powerful in that regard. It does a lot of information or calculations in quick time. Okay. This template here is something you can change, and MATLAB is again advantageous because it gives you so many templates to try for your data. So when you acquire experimental data or computing data or whatever type of data, you may or may not know what is the underlying pattern. You might not know that it's a quadratic, you might not know that it's exponential or whatever. So you can try different functions and to see which of them is actually a better representation of your data. That's how you practically do it. So now let's try problem 17 point, the last problem in that unit, 17 point something, 17.31 using MATLAB. I want you to type in the x values, type in the y values into MATLAB, and then we'll go from there. Those who are trying. So what I would do is minimize this, go to my command window. I'll define, say, x1 equal to, let's see if I have a copy of the textbook here. What are the x values? 0.1. I'm trying to see if I can copy paste it. Yep.
0.4.
Yeah, I was able to copy paste it. So I got x1. I mean, of course, those who are typing it in, please do that. I'll wait. So x1, I'm just calling it x1 because I already used the name x. If you want, you can use x again. It's okay. X1, and then I'll define x2 or y1 equal to open square bracket these values. So I have x1 and y1 entered into the workspace or the computer's memory. So if you are up to here, next step continues in the curve fitting app. Okay. You have a question? So when we do statistics, which is module 6, we will use this app, as well as there is one more app in MATLAB called distribution fitter. So we will use both of those at the time. So although for the purposes of exam 2, this may look like not exam relevant, it is still course relevant. Okay, so don't completely miss the bus on this thinking it's not important. All right, so then I want to get my, curve fitting app. Okay, I'll open a new fit, new session. Don't save. Or maybe I should have saved, sorry. All right, so now step 1, select data. What is my x data? x1. Y data is Y1. Y1. Okay. Now, first observation, the data doesn't look linear. And of course, the linear fit doesn't capture the trend because linear means it just decreases monotonically, whereas the data reaches a maximum and then decreases. So initially it increases, then it decreases. That's also qualitatively not correct. And this is not a new problem, by the way. We did this problem last lecture. This is also problem 17.11, which we did by linearization. Today we are going to do this as non-linear regression. So if we do polynomial, if you actually read the problem statement here, they are saying in problem 17.11, we used transformations to linearize and fit the following model. Now they are saying use nonlinear regression to estimate alpha and beta based on the following data. So they have given you a template which you can enter into MATLAB and ask MATLAB to evaluate the constants alpha and beta for you, which is also done using the principle of least squares regression. And even if you don't do the derivation now, MATLAB has everything programmed in. That's the power of a software. Okay? So go back to MATLAB, and wherever you have the fit options. So if you go here, we want to choose custom equation. That is, custom equation means entering your own template function for MATLAB to fit. Okay. So here is your custom equation. What do you want it to be? You want it to be A times X multiplied by exponent of Bx. Yeah. No. Let me just make sure I got this right. Alpha x times exponent of beta x. Yep. So first of all, look at the fit here. It nicely follows the data at all parts of the data set, at low values of x, at higher values of x, and so on. And our fit equation is ax times exponent of bx. So question becomes, what is the value of a and b? And if you see here at the bottom, you see here at the bottom, a is 9.8971, b is minus 2.5318. For your homework, you were asked to figure out the same values but using linear regression. Does anybody have those values? Can you check if these agree with your estimates? Yes, no. Has anybody tried homework 3, problem 17.11? Not yet. Anyway, you can try it, and when you do, you can also use MATLAB to verify your result. So anyone submitting solutions with wrong values is inexcusable, because you have MATLAB, you know how to check it. If you didn't check it, it only means one thing: you're lazy. So answer is right here. You are asked to arrive at that answer using another approach, so you can cross check. This makes sense in the sense you are step 1 feeding data, step 2 choosing a form of the fit equation with some missing parameters that need to be evaluated, and then letting MATLAB evaluate those things. Okay, it's sort of like using the software. Okay, so